So today we're learning from Roxana Bujack, a staff scientist in the Data Science at Scale team. She studied mathematics and computer science and received her PhD in image and signal processing at Leipzig University. She'll be telling us about her work on color perception. This has much to do with how visualizations of data that the lab uses can be as useful as possible to the scientists needing to understand those data. Roxana has been at the lab for about 7, 8 years, maybe going on 8 years now. And she started in the position that she's in now. So we got her early, folks. This is really great. Before then, she had a postdoc at UC Davis at the Institute of Data Analysis and Visualization, and at the Technical University Kaiserslautern Computer Graphics and Human-Computer Interaction Group. So everybody, let's welcome Roxana Bujack.
Thank you so much for the lovely introduction. Thank all of you for coming. This is like super nice. So yeah, so Linda told me it shall be a conversation like at a party. If somebody asks, hey, what are you doing at the lab? I think I will not be invited to this party again when I say, good that you ask. I happen to have this slide deck with me. Let me turn down the music a little bit so you hear better what I have to say. So yes, I have the slide deck, but still, I try to focus on just the fun things about this research, and there are a lot. So it goes back to a paper that I wrote together with Emily Teddy, Jonah Miller, Electra Caffrey, and Therese Turton, whom I really want to mention and say thank you for all of your contributions to this work. Jonah actually being here. Thanks for coming. All right, so the coolest thing about this whole research is actually the media attention that it got. And one of the things that's my really favorite, because it's from the Albuquerque KOB4 news station, I want to share a minute of that with you, just because it's the coolest thing that ever happened to me. So. I mean, the kids are good, right? But that, all right. Okay, so yeah. So the woman starts really saying, and it is not every day that you can prove a Nobel Prize winner wrong. And so here we go. So that was the coolest thing, but there were so many other things that happened. So the lab very proudly wrote, we proved a Nobel Prize winner wrong. And I was like, when I need funding, it's I, right? Now it's we. The Schrödinger was wrong, all kinds of things. It showed, I was invited to a podcast, and I was on the Hacker News. And this guy that I've never seen before said on Twitter, Roxana Bujack sticks it to Erwin Schrödinger. And I was like, oh, that's maybe a bit harsh. Well, also the article was like translated to 20 different languages, and it was like really, really cool. So today I just want to take you on the tour and show you how did all of that happen, right? Maybe the first question is, why would the lab care about color perception, right? Like, why do our taxpayers pay for something like that? And the answer is that all the application scientists, the physicists and such, right, they run giant simulations that they need to understand somehow, right? And us visualization people, we make pictures that hopefully help them to understand their data. Color mapping is probably the most common method to look at least two-dimensional scalar data. But the utility of such a color map visualization is strongly linked to the quality of the color map that you use. So what you can see here is the temperature of the ocean surface, and it's the exact same data on both pictures, right? They're just visualized with different color maps, the rainbow and the grayscale color map. And when you look at this picture here, for example, you think that as you traverse north, right in this direction, there's a huge drop in temperature, because you like go through this yellow so quickly. But if you look over there, you can see that there's actually nothing happening there. The thing that you see, we call this an artifact. This is just happening in the color map. It's like one of the problems that the rainbow has. It's not perceptually uniform. Yes, we had an artist actually employed at the lab that would like nitty-grittily make beautiful and really good color maps. But the question was, is there maybe a way to automate the work that she does? And that was our task. So that the scientists get like good visualizations, but can still somehow use their beloved rainbow color map, even though it's like harmful. And so we said, oh, sure, we can totally do that because a color map actually is a mathematical construct, right? And therefore lends itself really well to automatization and generalization. A continuous color map forms a curve through color space. And so we can analyze its properties by means of geometry, right? So it maps your data to a color. And color mapping, the whole process itself, is actually a concatenation of two maps. The first one is your data that goes from the domain, right? So from Earth to temperature. And the second one takes temperature, goes to color. And to illustrate what's going wrong in this visualization here, I use a 1D analogy. So assume your data domain is only one-dimensional, it's just x. And you have f of x, this is your data. In this case, it's a parabola, right? Now, you take this parabola and you put it into your color map. In this situation, our color map, it's a function, right? It is this sine function, right? Then the concatenation gives you this snaky line. You look at it and you think, oh, my data is a snaky line. But no, it actually is, it's a parabola, right? So if your color map were linear, then the same problem does not happen, right? And the grayscale is pretty much linear-ish. So you do not see those weird effects that can come just from the color map. So we thought, yeah, great. So we need something that is linear, right? But actually, it's not true. So this color map here is one designed by the artist that I mentioned. And this one is like the closest linear approximation to that one. Not only does it look ugly as shit, but also, it does not have the same kind of contrast, right? You will not see the same little tiny features in your data that you see when you use the good one. So there are competing requirements when it comes to the design of a color map. You want high discriminative power, high contrast. You want order. The idea is that even if you do not look at the color bar, that you would know what is high, what is low. You want uniformity so that the distances in colors reflect the distances in your data so that you perceive the shape correctly. And you want smoothness, the thing that happens at yellow, right? It's not smooth there. The color map like makes a quick jump there. That is why it looks so weird. And yes, so we said, this is awesome. We can do this. We use differential geometry because in differential geometry, we can describe all of these things mathematically. But in order for it to be meaningful, we need to use a space that really reflects human perception, right? If we use differential geometry in a space that does have nothing to do with how we see colors, it's meaningless. And this is when our journey began, and we dove into the theory of color spaces. And that is really super, super cool. So color per se is a physical phenomenon, is infinite dimensional. Because for each distribution of wavelengths over the visible spectrum, you pretty much get a unique physical color. But for us humans, it's only three-dimensional because we have three different type of color receptors, like one approximately around blue, one around red, one around greenish or so. So infinitely many colors get projected down to this three-dimensional space, which we know as color, right? And the first one to really like mathematicalize this was probably Hermann Grassmann, who described color as a three-dimensional Euclidean vector space. So there you can describe mixing colors by adding vectors, by adding numbers, right? So super helpful, 1853. And that was just the theory. it actually took much longer. Like in 1920, the actual experiments were done to prove, yes, this is really 3D. We can like figure out exactly which contributions of those 3 receptors correspond to which wavelength exactly and map that space out. And that gave birth to the modern color spaces, mostly moderated by the CIE. But there are a bunch of experiments, bunch of observations that do not really fit into this model. For example, when a color's intensity is decreased, so you use the exact same wavelength distribution, you just tone everything down a little bit, you see changes in hue. Whereas this theory would think, yeah, you see the same thing, right? Same when you mix a color with white. And this is my favorite experiment here. It's called hue superimportance, and I will explain this in a moment. You have like a circle in color space around the different hues. So in the middle there's gray, right? And you go around the hues. And you ask the people like, how many colors do you see? And you do the same thing of going from the circle to the center of the circle. Like how many steps would you have to go to end up in the middle? Then this circle would have a circumference of about 4 pi times the radius. And that is something that is totally not okay with Euclidean geometry, because there, probably everybody knows it's 2 times pi r, right? So you can still imagine it as being like a crinkled fan kind of thing, so that just you get like this large circumference into this situation. And that is what motivates color as a Riemannian space. And so those were the experiments, right? This is the theory on color as a Riemannian space. So Riemannian space can be curved, so it could encompass this weird shape that makes it larger on the outside than on the inside. And yeah, and the theory here actually significantly predates some of these experiments, super cool. And Riemann himself, right, the inventor of Riemannian geometry, in his paper in which he invented it, actually said he thinks that color is one of the examples for a curved space. Later Helmholtz was the first one to really map it out and give it numbers, and Schrödinger gave a nice definition of hue, saturation, and value by means of this Riemannian space. So you have to imagine how super, oh yeah.
Would you define again for me what color space is? What are the dimensions? Or how might I visualize it? I'm not doing well.
Okay, so how do I put this? So color space is a mathematical approximation of what you can perceive with respect to colors. So a color space would have to have one coordinate for each color that you can see, and it should have a relation, a distance, a metric, right, that tells you how far apart you perceive certain colors. So if you have the space with the coordinates, right, then you can start to communicate to other people about color without having any communication issues, right? And if you have the distance, then you can answer more complicated tasks, like the one that we want to ask with the color maps, or like questions of, I want to build this car, and I want the outside, color to be at least this close to the color of the inside lining. Does this still work? Kind of for these questions. Does that make sense?
Yes.
Awesome. Yeah?
Well, on the computer, we're used to seeing 255 levels of the 3 different colors, and that's where you get the 16 million different colors. And so you can have all the colors to be the same value, but you can take that value and lower it, and that's where you get hue.
Yes. It's just that if you use that with a normal space, like the ones that we are used to, RGB, CMYK, or maybe even HSV for the little more sophisticated people, those are very coarse approximations because they are all Euclidean, right? So if you do that, you think this is what's happening, but actually there are deviations from what you think is going on that do not consider these effects, right? So the thing, like if I add white, right, I actually get a different hue. That is a trap that you would step into if you use the RGB model, for example.
Well, so does this get around the fact that, people, very definitely, people in their eyes perceive colors very differently sometimes? What you perceive as pink, and as an artist, I run into this issue. So this mathematical thing, this is a way to get around the differences that people have in how they perceive color?
No, this is not. What we're talking about is really a model that tries to mimic the average of human color perception, not an individual kind of thing.
Got it.
There is a certain deviation, that is clear for sure, but we're still struggling with the average thing. So
Yeah, but what about when you're hallucinating? You perceive colors in a very different way also, right?
I do not know that. I trust you. So it's about perceptual color space. We do the hallucinating color space another day.
It would be interesting. It's an interesting experiment.
Probably.
You get some volunteers.
All right. Are there other questions up to here? Then, all right. Yeah. So I did my literature research, and I got super, super excited. Because, I mean, you come across all these super famous people. They're all German, right? I really felt like this is destiny. Because I studied math, right? So I really understand what's going on here. I do visualization, so I really need that thing for my day-to-day job. But also, I am German. I'm actually able to understand the paper that these guys wrote, right? I was like, wow, this is amazing. This is going to do something big. And it did. So here's our big break, the non-Riemannian nature of perceptual color space. So I read one paper by a scientist called Judd, and he summarized all these experiments, like some I mentioned already, that are in violation with the theory of a Euclidean color space. And he also mentioned another experiment, or another phenomenon that is called the phenomenon of diminishing returns. So this thing, maybe you have heard it in the economy situation. It pretty much means if you drink 2 beers, you're not twice as happy as when you drink 1 beer. And it kind of, it kind of goes down in the end. And the same phenomenon happens with color perception. If you give a person 2 colors that are really far away, so for example, we have on point A a blue, and in point C we have a red, and we ask the person, how far do you think those colors are apart, right? And they assign some number, let's say 10, doesn't matter. Then we take the shortest path from A to C, speaking about the Riemannian model, right? And take the middle on that thing and get some color, purplish, that we call B. And we ask again, how far do you think those colors are apart? They will not say 5. They will say something like 7. So that when you add those things up, you get something that is significantly bigger than the original distance that you had. And this phenomenon was seen by 2 experimenters, McAdam in '63 and Helm in '64, probably independently. And when I read that, I was like, oh, but actually, that cannot be modeled in a Riemannian space. Because a Riemannian space, even though it can be very curved and complicated and something, what is definitely true in there is that the distance between 2 points is the length of the shortest path that connects them. So if I start walking from A to B, and even if I go through some Escher-like painting, right? If I count my steps at B and keep on counting my steps all the way to C, they will add up. There's no way around that, right? So as a mathematician, I was like, okay, so it's not Riemannian then. That's cool. So we need more complicated algorithms to actually do what we wanted to do. And I wanted to sell this, right, to people to fund us and in the paper and stuff. So I wanted to cite a paper that really says it. And to my huge surprise, I couldn't find it, right? There was no such thing in the literature. And I was like, this is crazy. What's happening here? It got even more crazy because McAdam himself, the inventor of diminishing returns, he wrote like 15 years later in a paper, there was no strong evidence that those conditions for representation by Riemannian space are violated. So it looks like he himself did not see that this is a contradiction. And I'm like, okay, cool. What's going on here? Like, how's this possible? And we kept digging in more papers and more stuff, and I found it's actually pretty controversial because we found 4 papers that saw diminishing returns in their experiments, but we saw also 1 paper that saw the opposite, and an overwhelming amount of papers who saw neither. For them, it added up just fine, right? And I was like, oh, crap, now, what do we do? So we probably have to do our own experiments to verify what's going on. Because interestingly, there was a scientist called Ramsey, and he said, he was one of the ones that there is no diminishing returns, and he said probably those guys who saw it, it is due to poor experimental setup. Because this question, when you ask people, how far do you think those colors are apart, give me a number, is a very difficult task. Like there's a lot of jitter, like it's hard for people to say that, right? So he said it's possible that they saw this because people are just so unreliable in answering that question, and they should have used a 2 alternative forced choice method, where they just say which one is bigger, because that's easy, right? And with the right mathematical model, you can derive the actual numbers from that. The Ramsey story is also funny because he was a PhD student of Helm. And so he totally pushed his supervisor under the bus with his paper saying it's not true. So we did that. We went out and did our own experiments with the 2 alternative forced choice. So we give the observer a triad, like 3 color patches, and just say which one is more different from the middle, the left one or the right one. And here you can see 2 of these triads that actually have the same difference of differences, right? So if there were no such thing as diminishing returns, people should have the same accuracy for the top triad as for the bottom triad, right? But maybe you will agree that the bottom one is much harder to answer, right? So I'm pretty sure that there is diminishing returns just from looking at this little example. But we ran the whole big thing, and we found that as well. So that's the result we got. Diminishing return exists, even if you use the complicated experimental setup, right? It is in contradiction with the paradigm of a Riemannian space. Therefore, color space is not Riemannian. I mean, perceptual color space, right? Okay, so let's get back to our original question. Did we prove a Nobel Prize winner wrong? I mean, taken word by word, I think you could say yes, because Schrödinger was an inventor of the Riemannian model, right? And he was wrong. But it is a little bit misleading because you might know that Schrödinger did not win a Nobel Prize for his color theory, but for quantum mechanics, right? Could we say that Schrödinger made a major error, that he was like horribly wrong? I do not think so, because the step from the Euclidean model, right, to the Riemannian model was such a forward-thinking and super smart approach, right? It got us so far along the way. It explained most of the experiments that were not even done back then, right? It was really amazing. So I think saying we proved him wrong is not fair. We should say we were able to, further his work, right? And maybe it would be more fair to say Schrödinger was almost right. So all right. So that brings me back to the conversation part, I suppose, because it's the end of my slide deck. So I'm happy to answer any questions.
What is the image on the far right? That's beautiful.
I have no idea. It is the image that was under the Twitter thing of this guy's.
It looks like pop art.
It looks really pretty, yes, and many of the articles that came out had some kind of really cool thing. I suppose they just put color into ChatGPT and put out whatever they got.
Could you back up a couple slides where you had the 2 triads?
Yes.
So I might have misunderstood you, but you said the bottom one was harder to distinguish whether the left or right is more different?
In my opinion, it is, yes.
Because to me, absolutely, the bottom is easy, and I can't tell on the top.
Really?
Yeah.
I mean, it might also be due to the presenter and stuff. Really, like to me, this one looks like these two look almost the same, and this one looks much brighter to me. Well, that totally goes back to the.
I agree with him.
Did I-
I think the bottom one is much easier to distinguish.
I mean, it's easier to distinguish from the middle, right?
Yeah.
But the question is, which one is further away from the middle, right? That's the task.
The right.
Yeah, I still think the bottom right is the furthest away.
Is the reality that they're both equidistant from the middle, and it's just how you perceive which one's further?
No, they're not equidistant. It's always the right one that is further.
Okay.
I mean, please take these numbers with a grain of salt, right? Because the measure by which we measure the distance here is the measure we're trying to trash, right? So this is just a ballparkish thing. We do not really claim that this one really is further away. By the old measure, this one is further away and maybe far enough to be somewhat reliable, right? In the evaluation that we do not really take these numbers into account. We only go by the diversity of the answer, right? So the closer the people go to random, the closer they say 50-50, this side and this side, right? This is the measure that we take to figure out how far the distance really is. So we do not use these numbers. These numbers are just so that I can explain to you. Let's assume, this one and this one are, so here, from here to there, it should be 20, and from here to there, it should be 25 steps, measured in the CIE delta E. So the distance of difference is, right, so the 20 and the 25 is 5, which is the same as on the top thing. But of course, it's only a very ballparkish thing. And the top thing, so we have a distance of 5 to the left and of 10 to the right. So usually you would say, oh, look, this one is twice as far apart, from the middle than the other one. So usually it's easier for people to answer that question, while this one is only, 5, 6, 4, I don't know, apart. So you could look at it from that perspective.
So following on that, this is, colors are physics, right? They are what they are. You're talking about perception of people. And you did mention a little bit about variation in people. So how much really is that compared to what you're getting with your average results?
Yes, a very good question. So there is a huge variation because we have people who are color deficient, right? And for them, the perception, of course, is significantly different. So what usually happens is they have only 2 out of the 3 different receptors, right? So for them, color space is only 2-dimensional, and depending on which one is missing, right, it's like a projection of that thing to even smaller space. So for them, it's significantly different, right? Also, there is a known difference that comes with age. The older we get, the more our retinas get kind of yellowish, and so we see things differently. But from like healthy people with not too much of a spread in age, the difference is actually not super big. So when these experiments were done, I do not have a picture for that here, but these ones here with these curves, right? So I saw the picture that had all the curves on top of each other of all the different participants in the experiment. And they looked surprisingly similar. I would say there is like a 10% deviation away from these standard curves. It's really surprisingly similar.
A couple of questions. One is I intend to be a little bit amusing. Back on the slide that you were just had up there.
Which one? This one?
Yeah. So 320 triads, I think I understand what you mean, 250 different participants. Each participant, how many triads are they having to look at before they go crazy?
I don't think we had anybody go crazy. I think we had them look at about 50-ish
Okay.
thing. I do not remember the exact number,
That
but
might
it was
be-
okay-ish. I think it took them like 20 minutes or so to do the thing.
Okay. I could maybe do 50 without going nuts, but I don't know. My other question though is what about some sort of a validation? I'm thinking, for a particular participant, let's say you've got a really hard worker that looks at maybe 80 triads. What if you have interspersed in there randomly the same triad presented maybe a half dozen times? How similar are their scores when they look at the same triad at different times in different circumstances?
Ooh, good question.
Good question. I cannot answer this question. What I can say is that we did a bunch of sanity checks with
I know what you mean.
with of the people,
Yeah, I know
right?
Oh, no.
So.
You meant sanity.
So, for example, we first had a round in which we taught them the task, right? And then we showed them some things that were super easy, and we checked did they understand it or not, right? We also had them self-identify if they were color deficient, right? And we also had them do the Sahara test to see if they were, the thing with the number and the bubbles and stuff, and only allowed people who had that. Also, we only allowed people who were sitting in front of an actual computer and not on a phone or something to do these things. And if we had people who were answering always on the right, or that would be worse than chance, then we discarded them and figured they just wanted to earn a quick buck and did not take the test seriously. So had them filtered out as well. So there were a few things. Also, we had I know that we have the triads sometimes on the left to right and the left to right switch to see how that influences the stuff. So we had a bunch of sanity checks that we could look, is the data really trustworthy or not? But I cannot tell you off the head easily what the stats were on this. I can figure it out for sure, but I don't have the data here with me.
Was there a difference, eye fatigue? Were there answers toward the end of the 50 things?
No, there was not. What we thought actually is that people would get better over time because there is a learning effect, right? In order to keep them interested, we would actually tell them if they were right or not based on the old model, right? And so we thought, they would want to play the game more and really want to get it right and stuff. And we thought that would help them to actually learn, that they have to be more careful when the things are more apart. But there was no statistically significant effect of early or late at what time they saw which pattern.
So can you go back to the map that shows the temperature of the ocean at the very beginning?
Sure. Oh, here.
Yeah, so what you want to do is you want to convey something that's realistic. So the one on the left is hard to understand because it doesn't agree with the one on the right. But you can take your color map and you can have multiple points in there so that you can make the color map nonlinear. And so you can move the colors in space in order to make the color map agree with the gray level. But you have to let people know that you did that because you manipulated the colors. The intensity, yellow versus red versus blue, you slid it around. So as long as you let people know that you manipulated for emphasis, then I think it's okay to do that.
Yes, definitely. So it's of course absolutely okay to choose a color map that is nonlinear or not even close to linear, depending on your visualization task, right? So the task that I mostly have in mind when I think about this is to really accurately portray the shape of the underlying color, right? In which situation the uniformity of the color map is really important. But, and that is absolutely correct, there are many other tasks that scientists have when they make a visualization, right? So for example, there could be something really, really important happening exactly like here, for example, this cool von Karman vortex street behind this island, right? It looks so nice, right? Just because it happens to be exactly in that temperature range where we have a lot of contrast, where the color map moves so quickly that you can see all of these details, right? So for a scientist who wanted to emphasize this thing and talk about this cool feature that happens here in the middle of the ocean, right? He would actually purposefully want a color map that has a huge contrast, a very high discriminative power, as we call it, in specifically this region where the feature is he wants to highlight, right? So then, of course, the requirements for your color map are completely different because it's a different task, right? Still, being able to understand your color map mathematically is going to be very helpful for you to also target this task at hand at that position.
So mathematically, you have to tell people what you did. And as long as you tell them why you did that, then you can come up with any mathematical pattern that makes sense.
I mean, in limits, right? I could show you something really horrible. I make everything black and I say I made everything black, but here's your visualization, right? So even with full disclosure and with the full mapping of the color bar, right? There are still things that are not really sensical because they do not really feed into the way that we as humans understand data well.
So the James Webb, they're collecting images in the infrared. Yet when they scale it, it goes from blue to red, and the whole rainbow in between. So they're manipulating the colors that they're projecting of what they get from the cameras.
Yeah, of course, right? Otherwise, you cannot see anything if it's infrared, right?
That's right, everything is red.
Or not even. Yes, yes.
With different frequencies.
Does it make a difference? I noticed you had a color bar up there, and I think, are you talking about Francesca Sanzel?
Oh, yes, indeed.
I know Fran very well. So you had a color bar up there that showed sort of a gradation from white through yellow, through orange, through deep red. There, that one.
Yes, that is Francesca's.
And you know, as we look at that, to me, it's like, that's all in a family. I can see the gradations much more easily than I can when you use the full rainbow spectrum. Those are just too wacky different, and I don't know the difference from purple to orange, but I kind of know the differences in there. So how does that play into what you're talking about? Because I think Fran would choose something like that.
She designed it, right? She made this one.
Right.
She was the one who made that one. So how can we...
Are you arguing that, well, you were talking about how it all plays out mathematically, but are you suggesting that, in fact, what Francesca is suggesting is a better way to show because of how we're perceiving color, or we're not perceiving the differences in color, and what it's not meaning to us when we use that full rainbow spectrum as opposed to that?
Okay, let's try one thing at a time. So I think, yes, Francesca had it right? She, as an artist and as a designer, just had this gut feeling of what would make a good color map, right? And she applied this to make that thing, right? She is hella expensive.
Francesca.
Exactly, right? So now we want this thing that's as beautiful as that one, but it's supposed to be green and blue and purple, right? So if we call Francesca and say, please do this for us, it will cost $10,000, right? So the idea is if we can cast it in math, right, we can automatically do this. And that was the goal that we had, to replace Francesca. No, it sounds mean. But actually, we never got there. Because when all this stuff happened here, we got completely sidetracked, and we were like, no, this is the biggest thing. We have to like jump on that and just do this. And so within the 2 years we had this project running, we never actually got to do what we wanted to do to really implement the improvement. So it's only there for Euclidean spaces still.
Are you going to be able to continue?
I don't think so.
No? Why? Because you need more funding from somebody to do it?
Exactly. So color map improvement, even though we could kind of justify it with the application scientists and the stuff, it's still kind of far out for a weapons lab, right? So the only reason I think we got this funded was because it was through this early career thing where they try to push people, even if their ideas are a little bit crazier, just because they want to help them in their career paths. So I think they took pity on me and allowed me to do the research, and they would never do it again. It's my guess. Would be great though, if anybody of you has funding control, right? We still want to do that. Yeah.
So that gradient that's on the top left there, it looks more, what I would say, like, as a 2D, from a white to a dark red crossing through the yellow line. And then the computer model is trying to do that in 3D, right, with that visualization in the bottom. How does that compensate for the difference in, I think it was a couple slides forward, you had the 3 different intensities that human perception was, colors. How do you compensate for that?
Oh, yeah.
So, okay, let's maybe try to start there. No, wrong direction. Here, with that one, exactly. So these are the experimental results that we got. The experimenters actually, right, so they showed a single wavelength on one side, right, they like put the white light into a prism and showed this on one half, and on the other side, the observers had like 3 knots with which they could steer 3 primary colors that were approximately here, here, and here, and they were supposed to match the exact same thing they saw on the other side, right? And this data, like where they steered the knobs, is the thing that we see here in this chart. So in order to get a wavelength of 500, okay, that's a poor example because we have this weirdness here, of 600, right? You don't need anything of the blue. You need a little bit of the green and a lot of the red to make exactly this impression. Okay. And then we take these 3 curves, and instead of plotting them on top of each other in 1D, we assign an axis to each of them in 3D space. And then we plot the 3 coordinates we get, you know, how much blue, how much green, how much blue, onto this specific location. And then we get this crazy bowish kind of thing. It's a line actually, it's a line in 3D space, and that is the boundary pretty much of our visual spectrum, because it's bounded by the pure one single wavelength impressions. So you know that if you take each of these points and you connect them with the origin, which would be black, right? Then you get like this cone kind of thing. And inside of this cone are all the colors that we can perceive. And then you cut this thing off at some kind of intensity. Like here they put the plane through the Maxwell triangle, cut that thing off and say this is the maximum intensity we allow, the maximum energy we allow that thing to have. And now we have this funny shape that looks like a horseshoe that gives you a 3-dimensional color solid that is now this first modern color space in which all the perceivable color have a unique coordinate. So we can exactly say this is that color, X, Y, Z. And in which if you mix 2 colors, so if you like put a flashlight on the wall and put another flashlight right on top of it, so if you add them up, right, all those mixed colors form straight lines in that space, right? So it's a really nice way to organize the colors, right? To embed them into a space that is meaningful mathematically and useful. And so now we are there. And now what is your question? How does that, with the 2D thing? Oh yeah, and then in that picture, I look at that. And then I look at this color thing. Then there were some transformations made to that because the distances between the colors did not map to the perceived distances. So they did some transformation and some adjustments to get like the closest Euclidean shape, right, to the actual perception. And that looks kind of like this when you look on it from the top. So you have white, the gray axis right in the middle here when you look from the top down. And the rainbow pretty much goes around in the circle or thing on the outside, right? So this thing is not this thing. This is just an example of a curve that goes through this space for illustration purposes. So does this answer your question?
Sure. Is that white curve the representation of like one of the gradient paths, or?
No, this is just some curve I put in there to say, hey, color maps form curves in color space. Sorry, this would be a color map that would be isoluminant, right? So this one goes from like light to dark, right? This one, since it's just flat in there, would have like approximately the same luminance. And it would just go rainbowish from blue to pink to red to green. This is how it would be if it were meaningful in any kind of way. But I just threw it to say, hey, it's a curve. Yeah, but you can plot all of these gradients actually and look at the shapes that they form, right? And actually, yes, that is the whole idea, right? Can we, by looking at the path, derive information about their quality as a color map themselves, right? So just we don't want to look, we want the computer to look. Want it to do the thing.
Going back to the slide with the RGB wavelength of that approximate cone, it looked like for a moment that red was negative, and I'm not sure what the y-axis represented, but what happened with the negative y? I mean, the negative red?
Yes, so very good question, but actually very explainable. So what happens is that if you take 3 colors as the primaries, right, and you want to mix colors, and you go along straight lines as you mix them, you get a triangle of colors that you can represent with 3 primaries, right? You can mix all the insides of the triangle of, like, so one of them was here, one of them was like here, and one of them was here. So we can map all of these colors. Everything outside of this triangle, we cannot mix with the 3 colors, right? So if you go through the whole spectrum, you go around this thing, and you will come across a lot of places where you cannot make them match, especially up here in the green region, because this is so far away, because it's so bent up there. And so what the experimenters did was they had also a replication of those 3 color guns on the right. So if it was impossible to make the color, they could just cast something on the other side. So if it was a really super saturated green, they could throw red on top of it to pull it more into the center, right? And then they would be able to match it. So in that situation, we get those negative values because the red was not added on this side, but on the other side, just to get it less saturated. So this is where these negative values come from.
So you can tailor the color map for each application, for each experiment that some scientist is doing and wants to see. Do you have a general solution that would be the starting point for all those color maps, especially for lab work?
Yes. So there are a handful of rules that we know that are reasonable to take. Like you want the high discriminative power, so you can see as many things as possible. You don't want these artifact kind of things. You want order, so that people know this is low, this is high. And you want the perceptual uniformity kind of thing, so you can really understand the shape below. And there are many good color maps that have a good trade-off between these qualities. So yeah, I actually had a few examples of popular color maps here. Yes, so the grayscale, right, is really nice except for discriminative power, right? It's super short, you cannot see much, but everything else, it does really, really well. This one here, the cool warm divergent color map, that is the default in ParaView. So ParaView is a visualization tool that was developed here at the lab, actually in my team, that is like a nice little tool. You just drag and drop your data in there. It has a bunch of filters that you can apply, like you can cut through the thing to see what's in the middle. You can draw ISO contours or all kinds of cool visualization things. And for a long time, it used to have the rainbow as its default, but they changed it into this cool, warm, divergent color map. The reasoning, I mean, the dangers with the rainbow we already saw a little bit. Reasoning is that this one really satisfies order super well because people have a natural understanding of blue kind of being cold, being on the low side, and red being on the hot, warm side, right? Also, it has like this white middle point so that you can kind of see how this is in the middle, right? And this is here or there. But also, it does not go all the way to like black. And for ParaView, this is particularly important because usually the data we expect we want to visualize is three-dimensional. And so we have shading, right? To see the shape of your, I don't know, car part, right? There is the whole computer graphics machinery that gives you the impression you're looking at the three-dimensional piece, right? There's light, there's shadow, there's reflections, all of this stuff. And that is on top of your color map, right? If you have really black regions in your color map, then you have high discriminative power for sure because you go all the way to black, right? But it interferes with your shading. And there are large regions where you do not see anything anymore of the geometry that you're really looking at, but you only see black, right? So that's also a reason for this one. Down here, this is Matplotlib's default, I think, Viridis, which is also a color map that is very good. It's very uniform and still has a pretty good discriminative power. It's a good trade-off between those two extreme differences, right? Yeah, so I think those would be good to-go color maps if you don't want to think about it twice. So the idea to really automatically improve color maps is if for some reason those do not work for you, right? But you want something specific. Let's say you are a scientist and there's a convention in your field that this thing must have this color, right? Because it has been plotted this way for hundreds of years. If you show up with a different color, people think you're crazy. So, right, so you want to use these colors, but still you want to make sure you do not show anything weird. This is where like the idea of an automatic color map improvement would come in handy.
Where did that bottom one come from, just out of curiosity? The Matplotlib, there it is.
Where did it come from? Yeah. So, I mean, the Matplotlib people designed it.
And who are they? That's what I'm asking.
I don't know the names. I think they're Americans, and they are Python enthusiasts.
And what field is it typically used in? Maybe that's the
Everything. Oh yeah, no, they're not application scientists. They are computer scientists that also wanted to answer the question, how can we get a good color map, right? And so they also like used a catalog of requirements that they wanted to have and designed that thing with respect to that. And a bunch of them that are similar, that go through different colors too. So like for them, they really wanted the uniformity part, but also they wanted a very monotonous transition in just luminance, so that if somebody who is vision impaired looks at the thing, right, or if you have a black and white printout of the thing, you would still be able to see what's going on, right? That was also one of the motivations that they had. So yeah, all of the color maps from that cohort look very similar in that regard. Yes.
You touched on a couple points regarding the quality properties of the various color maps. How do you quantify that or define that in terms of, I guess you kind of explained that a little bit, but is that like how you are starting to use the automated sorting or prioritization of the color maps?
So the way that we did it was also through literature research. We went through all the papers that gave recommendations of how a color map should look like in order to work well. And we collected all of the things that the people said. And it was actually really, really a difficult task because all the people use different names for the same thing, right? So, no, it's absolutely bizarre. And actually fun story, right? So you know Francesca, right? So at the beginning, right, I sat down with Francesca and I interviewed her. How do you design a color map, right? So that I would know exactly what to implement to do the thing. And so she said, yeah, good that you ask, right? So a color map has to be linear. Linear in perceptual color space, right? And I was like, oh yeah, awesome, yeah, that sounds really great, right? So I go, I'm taking her color map, right? I make it linear, I get this. And I go back and I'm like, Francesca, I don't think this is right? This is not what you want. She's like, no. This is not what linear means. Like, what you talk about is a straight line in the color space, right? That's not what linear means. And I'm like, Francesca, I mean, I studied math. I think I know what linear means. There's a general understanding. that it's this straight line kind of thing. Right? I was like, no, 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 no. What I mean is that for each step that you go along your data, right, you go the same size of step in your color map, right? So like when you drive along the path in your color map, your car has always the same speed, right? You have cruise control on, you never go faster or slower. That's what happens at the yellow, right? At the yellow, the rainbow goes really fast, right? And I'm like, yeah, this is not called linear, right? This is called parametrization by arc length. We have a good word for that, right? She's like, no, 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 I'm pretty sure. I'm like, okay. I will show you, right? I will go to all those papers and people that say, right, color maps should be linear, right? And say what they mean and show it to her. And I look at it and it's all over the place. So I would say about 25% of the authors claiming linear were on my side, 25% were on her side, 50%, I don't have the slightest idea, because they did not provide a formula. They only used the word linear, right? When I had first read all of these papers, I was sure, yeah, they mean linear, right? But now I've seen this 25% over there and talked to Francesca, I was like, maybe it's not what they mean, right? And the same thing is true for the other things. Order, right? Order, super simple. You want people to know what is low and what is high in your color map? The idea is you pick, like the argument against the rainbow is that it's not ordered. And I'm like, what are you talking about? This is just the whole like spectrum. It is linearly increasing in wavelength. There is nothing more ordered on this planet, right? How can it not be ordered? What do you mean, right? But they meant if you take 3 colors randomly out of that thing, you put them on chips and you give them to a user and you say, order them, that you don't get the same response from the people over and over again. But it's actually all over the place, right? Not everybody sorts them as a rainbow. Some sort them by luminance. Some actually sort them alphabetically. Right? So in that sense, it's not ordered. And like really, and so many people use different words like discriminative power, contrast, color space, exploitants to describe the same kind of concept, and you never really know, right? So we like made huge piles of gathering all the things and say, okay, from now on, all of these things we call discriminative power. And, and here is a formula that tells us what this means, right? So from now on, we actually can like communicate mathematically about the quality of a color map. But that is really new. So that was in 2017. And the quality guidelines per se, right, they go back hundreds of years, right? Like people drawing maps back then, they were making use of these properties, right? Like what is a high mountain, what is a low valley, what colors did they choose to represent this? They already used the exact same guidelines, right, to make the map readable and stuff, right? So all of these things are not new per se.
I think that was fantastic. Everybody, let's thank you.